Okay, hello, Science Father Award team members. It's with great pleasure to accept your wonderful Best Researcher Award on Composite Materials Design, and thank you. I believe that research is not a burden, but truly life. With this motivation, I have been engaged for almost 10 years in research and teaching practice in higher education. So part of it, this research award is delivered to us as a recognition to motivate us, to energize us. So that's the reason why I'm saying thank you, Science Father organization, for your wonderful and highly motivating research award. So our research was basically focusing on plant-mediated biosynthesis of copper oxide nanoparticles for enhanced catalytic reduction of organic dyes as an impact for sustainable chemistry, for sustainable green chemistry. Currently, I'm working as a postdoctoral researcher at the Department of Chemical Engineering, National Taiwan University, Taipei, Taiwan, and I'm a faculty member of Adigrat University, Adigrat, Ethiopia, and the distance between Ethiopia and Taiwan is almost 8,000 miles. It's very far, very far. So Ethiopia is located at the east of Africa, and Taiwan is in the Asia. A very wonderful country, highly impactful, with great researches delivered in this beautiful nation. So my bibliography seems this. Originally, my bachelor was BEd in chemistry from Wollo University, and then Master of Science in Applied Chemistry from Bahar Dar University. And after graduation, my master's graduation, I been joined to Adigrat University to be a faculty member. And since 2014, I awarded PhD scholarship at National Taiwan University of Science and Technology, and I earned my PhD in 2017 from the Department of Graduate Institute of Applied Science and Technology in this university. In addition to this, right now I'm postdoctoral researcher at National Taiwan University in Taiwan. I am also associate member in Royal Society of Chemistry and a regular member American Physical Society. I do have also some reviewing experiences from various journals such as SES Nano, Emergent Materials, Discover Materials, RS Advanced, SES Sustainable Chemistry and Engineering. Our research is focusing on green chemistry in catalysis. So the application of green chemistry in catalysis is very important for the industry because catalysis is highly impactful in industries, especially this time. Nanomaterial catalysts are very important for our daily life. So these nanomaterials have three important parameters: activity, selectivity, and separation ability. So to enhance this activity, selectivity, and separation, nanoscale materials are required, and we design our material, our catalyst, to be synthesized based on plant green synthesis to benefit from green chemistry. Why we focus on plants? Because plants have very essential phytochemicals that can act as reducing agent and capping agents, as well as many other functional properties. So when we come to the detailed one, plant-assisted synthesis of copper oxide can follow two procedures. One is the first procedure is based on electrocatalysis. The second procedure is based on photocatalysis. The first one is electron enhanced from the reducing agent and the catalyst, and the second speeded by the catalyst, and the second one is photon energy enhanced catalytic property. So basically, we focus on the first one on electrocatalysis using the plant. Why? Because it is green and easy to manage, easily can be scalable, and it is green. So we use the first scheme. We adopt the first scheme in our system. Why we choose this Carreton macrostachys plant in our research? Because this plant has some very essential and vital properties, such as acting as, there are chemicals, phytochemical, which act as reducing agent and capping agent, and this plant is environmentally friendly, and this plant is also widely available and affordable, because the affordability and availability can impact the economic value of the catalytic industry. And then the next, it effectively produces nanoparticles because of its phytochemicals. The last one has many essential functional properties that can enhance the catalytic properties in addition to this important properties. So the first work was based on the leaf of this plant, and the leaf was very successful in the catalytic property of copper oxide nanoparticle, and we got the chance to publish this paper in Materials Express journal, IPO publishing family. And thanks for my student Atnafu. The design was based on this schematic diagram. So we do have the plant, and the plant was washed and then dried and then powdered. And this powder was treated at 70 degrees C and filtered again to prepare the precursor of this solution. And this was mixed with copper nitrate grand solution, and adding sodium hydroxide to make it fast reaction at 30 degrees C and the pH 11, and then we find this solution, and this solution was cooled and centrifuged and then dried, and we find a powder, and this powder was calcined at 400 degrees C for 2 hours, and finally we found this pure copper oxide nanoparticle mediated by plant species. So the X-ray diffraction of our material with this one, and the GA has been done. This is the morphology, and this one is the ADX mapping. So we believe that we successfully synthesize our material with its keeping its useful properties. And then we continue to measure and characterize the main catalytic properties. As can be seen, the sample with reducing agent and copper oxide nanoparticle was successful to degrade methyl blue within almost 1 minute. So this research was very successful, and we suggest the industry and the academic approach. The results were summarized in this table, and as you can see, our results are highly improved compared to the previous literatures. That's why the reason we said we were successfully synthesizing this effective catalyst for the catalytic degradation of organic wastes from industrial effluents. The second one was methyl orange, and this is another organic dye. Usually we found it from industrial effluents, textile industry. So when we design our material, it is basically to apply in the industrial effluents to treat the organic wastes and to make our environment clean, because our end mission is to achieve green chemistry in the catalytic industry with a great impact. So you can observe that our material effectively degrade the organic dye, and it is suggested that industries and academia can adopt this approach and make it in a large scale for further treatment of industrial effluents to make green environment. Our result was summarized in this table. Again, these results are very important, and we found them highly appreciated results with enhanced catalytic properties of our material compared to the previous literature reviews. And we also check the reusability of this catalyst, because nowadays industries need cost effectiveness and economical procedures, economical materials. So because we concern on this, we have been testing the reusability of our catalyst. So you can see the diffraction pattern from before and after. So the pattern are quite similar with no difference. And this is the chemistry. The chemistry. So how the organic dyes can be degraded using this catalyst. So it's very important. The next work was published as a proceeding in chemistry proceeding in BPI, and the key material was the bark, in addition to the leaf, and not only the leaf but also the bark was successful in reducing, in enhancing the catalytic property of copper oxide nanomaterial for nitrophenol catalytic reduction and antibacterial applications. Because in this work, we confirmed that the bark-based copper oxide nanoparticle can have dual applications. One is in the catalytic reduction, and the other one is in the antibacterial application. So our work is also very interesting, green, and impactful, not in one way, but in many. So this was the synthesis procedure and the material design approach. So as you can see, we compare our catalyst diffraction pattern with GCPDS pattern, and you can see it's perfectly matched with the GCPDS diffraction pattern. This indicates we successfully synthesize our material and we apply to the intended purpose. So as you can see, this is very important result, confirming our catalyst was highly effective in catalytic degradation of the organic molecule. So the results were summarized in this table, and we were lucky we found very impactful result compared to the previous studies. And this is the antibacterial application of these materials, not only on the catalytic application, but also on the antibacterial medical application was successful, and we found this result is in treating the Escherichia coli to bacteria treatment. So this material can successfully inhibit the growth of this bacteria in the medical concept. As a conclusion, making the world more sustainable requires accessible technology and affordable, abundant materials. So while green chemistry technologies create more sustainable world, the plants are also affordable and abundant with a simple procedure to prepare the composite material, nanomaterials for catalytic application and antibacterial application, not only for this, even for many other applications. So based on this concept, our research was successful and science further choosing our work, and we found the privilege to get the Science Father Award. And I want to say thank you, Science Father, again. And I can say that great impact is begin from small but smart contribution. What does it mean? Our work is very small, but it is smart. Thus, industries and academia can adopt our work to further study and implement green chemistry concepts for the industry, for sustainable industrial applications. Thank you, Science Father, again. Thank you.